Many researchers approach complex dynamical systems by trying to decompose them into modular fragments. In systems that exhibit cyclical behavior, the assumption is that slicing a loop into smaller segments will provide a set of independent equations. If the whole is too difficult to solve, perhaps the individual pieces are more accessible. We can test this assumption using the Collatz conjecture, specifically the accelerated odd Syracuse map. This version of the problem ignores even numbers, tracking only the arithmetic transitions between odd integers. To analyze these transitions rigorously, we don't track the raw integers themselves. Instead, we translate the history of a trajectory into an algebraic object called a finite exponent word. The exponent word is a symbolic array, recording the precise number of halvings absorbed during each accelerated step. We extract two primary values: the total sum of halvings, denoted as k, and the word length, m. The exponent word serves as a bridge. It converts discrete arithmetic steps into a continuous algebraic structure, providing the framework needed to determine the exact properties of any sequence. The inverse Syracuse map is affine, meaning it follows a predictable linear rule. Because of this predictable linear rule, any finite sequence of steps can be combined smoothly into a single operation. No matter how many steps the trajectory contains, its total effect is always linear. We represent this effect with a 2x2 upper triangular matrix, encapsulating the word's history. The top left entry is 2 to the power of k, the total sum of halvings. The bottom right is 3 to the sequence length, and the top right is -c, the total affine shift. This matrix construction often leads to a specific type of analytical error. Because the matrix is composed of these parts, it is tempting to believe manipulating those parts, slicing or rotating them, will generate new, independent Diophantine equations. Three common operations are attempted: splitting the word into subwords, cyclically rotating the sequence, and Chinese remainder theorem parametrization. These structural operations do not yield independent constraints. The information within the transfer matrix is algebraically self-contained, meaning these manipulations cannot produce new information about the system. To see why these operations collapse, we have to define a cycle using the transfer matrix. In a genuine cycle, the map must take a starting integer y, and after the full sequence of steps, return that exact same value. We express this as an eigenvector equation. We multiply the matrix by a vector containing the starting point. For a cycle to exist, the output must be a scalar multiple of that same vector. When we evaluate this multiplication row by row, the underlying logic of the cycle becomes clear. The bottom row simplifies to an identity. It confirms the length of the word, but it provides no information about whether the sequence can actually close. The top row provides the actual constraint. It simplifies to 2 to the k minus 3 to the m, all multiplied by the starting value y, equals the affine shift c. We define the term in parentheses as the denominator, d. Since the starting value y must be a positive integer, the denominator d must perfectly divide the shift c. This divisibility condition is the minimal requirement for a cycle. If the denominator does not divide the shift, the trajectory cannot return to its starting point. The first attempt to find a more restrictive condition is affine splitting.
This involves taking a word w and slicing it into two smaller components, u and v. The idea is that if the whole trajectory is a cycle, the intermediate point between u and v must also be an integer. Researchers hope this midpoint creates a second independent equation. However, the transfer matrices form a monoid homomorphism. This means the matrix for the entire word is exactly equal to the product of the matrices of its parts. This product gives us a specific rule for how the affine shift of the whole word relates to the shifts of its parts. If the sequence is a cycle, the arithmetic naturally ensures the intermediate step is an integer. We substitute this concatenation rule back into the original divisibility equation to see if the two subwords produce new constraints. The system immediately reduces. The new terms are not independent. They are linear combinations of the original variables. They cancel out, leaving us with the same divisibility condition we started with. Splitting cycles provides no new Diophantine information. It confirms that the path stays on the integer lattice, but it cannot create a new obstruction. The second attempt involves cyclic rotation. If a sequence of exponents forms a cycle, then any rotation of that sequence, starting from the second or third step, should also define a cycle. This is often used in attempts to find a distinct algebraic boundary that a potential cycle cannot cross. But cyclic rotation is merely a similarity transformation of the transform matrix. The fundamental properties of the map, like the trace and the eigenvalues, remain unchanged. The new fixed point is just the original point moved forward by the transformation. The algebraic requirements are identical to the original case. Finally, we consider multi-step admissibility and the use of the Chinese remainder theorem. This approach uses modular congruences to track whether each individual step in a sequence lands on an integer. This also fails to provide new information. Admissibility is self-propagating. If the starting point satisfies the single congruence for the entire word, every intermediate step is guaranteed to be an integer. Whether we rotate the sequence or analyze its modular steps, we find the same result. All the structural information is already contained in the baseline matrix. These failures lead to a formal conclusion, the closure information boundary theorem. The theorem demonstrates that finite structural manipulation of a Syracuse exponent word remains tethered to the baseline fixed point. You cannot generate independent constraints by rearranging the word's parts. Visualizing this, the divisibility condition sits centrally, surrounded by rotation, concatenation, and admissibility nodes. Under algebraic manipulation, these outer operations collapse into the center. They describe the same linear relationship. It's tautological. Rearranging entries creates no new obstructions because the fixed point equation fully describes the underlying map. This realization shifts the focus away from finite algebraic manipulation. For genuine obstructions, we must examine the saturation dynamics of the affine state space. We determine if generated values eventually fill every available modular residue. Proving a cycle does not exist requires information that scales with the sequence length, rather than fixed modular quotients that repeat. The closure boundary indicates that finite algebra is insufficient for finding cycle obstructions. Solving the problem requires analyzing the non-finite dynamics of the state space.